Ready. Ready. Ready.
Hello, welcome to Enlightning. So glad to have you here, Duffie. So glad to have you here, folks who are live. So glad to have you here, people who watch the recording. It's such a good life and a good day.
Good morning. Good morning.
Good morning, good morning. Hi, Duffie. Thank you so much for coming on Enlightning today to teach us about Cilium. I'm so excited to learn. Yeah. Fun fact, during that whole opening intro, I have two fun facts about that opening intro. For one is I dance back here alone the whole time it's playing. Like, I just need to, I have so much adrenaline before the show. I got to get it out. And then the number two fun fact is if you watch that video of me writing this stuff, I go across once and then I actually drop to the floor, crawl to the other side, stand up again, and then go across. So you can kind of see my head go down a little bit on the side. That's
Nice.
an Easter egg. Yeah. But anyway, enough about me. Duffie, it's such a gift to have you here. Tell us about yourself.
I'm excited to be here again. I'm a field CTO at Isovalent. I'm a member of the CNCF TOC committee, and I would say that generally speaking, my MO is to make it possible for others to succeed. That's kind of what I love to do. So I'm just super glad to be here and talking about all of this stuff.
Super cool. The casual way you mentioned that you're on the CNCF TOC, which stands for Technical Oversight Committee. That's like that's a big deal. And so
It's
you're just like,
it's a fun, yeah.
yeah.
The TOC is super interesting, actually. In fact, this year at KubeCon, I got to talk about it on the big stage, which is the first time I've ever been on the big stage. And we did an update talking about basically what it is. So the Technical Oversight Committee is a governing body within the CNCF that is responsible for determining those projects that will be included in the CNCF. If you've ever seen the landscape photo, like we're responsible for reaching out to projects and also working with projects to bring them into that. Into sandbox or incubating or graduated one of those phases, and also helping those projects move between those things, helping them understand what the criteria are, how to meet that criteria, and how to basically build successful open source projects out of what they've come to us with, and all of those things.
How many people are in the TOC?
The TOC has 11 people. But
11 people, yes.
the TOC also has, it's very similar to like the Kubernetes structure in some ways, where the Kubernetes structure has like special interest groups. We have technical advisory groups.
People call
So
those
it's not
tags, yes.
tags, exactly, yeah. So it's not just us, fortunately. It's like us, and we have tags, and those tags can include a number of other people. We have things, tags focus on everything from security to contributor, to contributor experience, to across a variety of different domains or those sorts of things.
Yeah.
And so we can enable those tags to take on some of the work that as an organization we need to be able to accomplish, things like being able to work with those projects directly. Sometimes it's the tag itself that actually has the resources necessary to be able to support those projects a little better than the 11 people of the TOC, because if you look at like the number of projects that are coming in to Sandbox, it's an ever-growing number, right? It's so 11 people, there's no way.
if you have like an observability project trying to join the CNCF, you might reach out if there is a tag observability, I don't know, but like some sort of related tag and ask them what they think and then
Yeah.
use their recommendation about whether to do it. Cool.
Yeah,
That makes
exactly. Get
sense.
their recommendation and also enable them to work with that new project, right? Have that project present to Tag Observability. Here's what we do. Here's why we think we're, a good fit for the CNCF. Here's what we want to
Uh-huh.
get out of it. Like here's, et cetera, et cetera. Like have that conversation
Here's,
with Tag Observability. Have Tag Observability bring that conversation, bring the results of that conversation to us. We go back and forth, make a decision, have a vote, and proceed from there.
I love it. I love how everyone in the community has a hand. They're included. If for a reason a project doesn't get accepted, there's like a trail of like, well, here's where we've talked about it. Here's why. Maybe it's too much overlap with this project that's already in the CNCF. Like, I love it. I love open and honest conversation
Yeah,
in life in
to be fair,
general.
the CNCF is meant to be like something of a hotbed of innovation. So even if there is overlap between projects, it doesn't necessarily exclude you from being included in the CNCF, as you can probably have noticed from the landscape again. There's tons of overlap between projects. The reasons we wouldn't actually, it's an interesting point. The reasons we wouldn't include a project or allow for a project to enter into Sandbox are that the idea itself perhaps is not novel, is not a novel idea, right? The overlap is one thing, but having the same idea and the same implementation of the idea as another project is a different thing, right?
Yeah.
Another one is that like the project itself hasn't shown that it has that it has contributors from other companies or more of an open source mindset or governance model, wherein like you are actually bringing people from other companies. If everybody that contributed to the project is all being paid by the same company, it's hard for us to determine like is it a good fit for the CNCF, because fundamentally we expect that projects that are under that umbrella are going to be open source projects with contributions from different companies, and look at that and look at that project as a scaling mechanism, or look at inclusion as a scaling mechanism for those open source projects.
That's fascinating. And then do you consider projects like in the order that they apply, or do you
First
like
come, first serve?
first come, first serve? Or is it like, hey, we have a ton of innovation in the AI space, so we're going to prioritize some AI stuff right now? Like, which way is it?
I think
some third way.
It's a hard one for sure. I think that there's a little bit of both of those things. It's definitely a task that I don't think that we have worked a little harder to organize and things. But if there were an area of focus that we really wanted to focus on, right, and that's absolutely where a tag would come in handy, right? Because we would say, well, let's build. We have enough of a ground rush of AI interest that perhaps what we should do is gather a number of people in our community that are focused on the AI domain, put them together into a working group or perhaps a tag, depending on what we consider to be the scope of the work. And then, have those folks have those kind of folks form up and start working on white papers around the subject, those sorts of things. And then from there, move on to helping us act as an advisory board for or an advisory group on that particular domain, right? Like what projects do they think we should include in the CNCF? How do we reach out to those projects? What projects do we see that are focused on the open source components of that particular domain, et cetera?
Cool. We have a couple awesome folks here in chat. And those of you who are watching, please do say hi. We have JavaCrunt. Deshaun's here. Hi, Deshaun. Thanks for being here. And Spheric is here. Hi, Spheric. It's great to see you. Spheric always has great questions. I'm going to, we should get into the matter at hand, which is Cilium, which is eBPF CNI implementation, which CNI is a container networking interface, which we did have a CNI discussion. So Duffie, this isn't your first time on Enlightning. You were on last month or a couple months ago teaching about Kubernetes networking.
Yeah.
And So I just dropped a link to that episode in the chat, so you have that as a reference. And anything we talk about from that episode, we'll at least like explain the acronym and give an overview, so you can still be here with us today. But if you want to dig deeper into some of those general Kubernetes networking concepts, we've learned from Duffie already. And then we have some other links I'm going to drop in the chat. Let me ask y'all who are here, what have you touched Cilium yet? And if so, like, what's your experience been like? Like, what would you like to know, Duffie, about people in Cilium and maybe eBPF?
Yeah, I'm curious, like, if people have explored Cilium as a solution to their Kubernetes networking space, and what they have experienced as far as like what eBPF is and those sorts of things. In this discussion, I'm going to be introducing eBPF in the context of like what we do with it at Cilium, and then I'm also going to be talking quite a bit about how Cilium does its thing in the container networking space, and then we're going to get into like some of the service mesh use cases. So it'll be really fun. Oh yes, cluster mesh is another really good one. Yep.
So, oh yeah, I have no idea what that even is. So we'll talk about that. Love it, love it, love it. And then I'm dropping some links. I'm putting in a link to the eBPF documentary, which I haven't seen yet personally, but I've heard it's amazing.
It's really good.
I'll be watching it probably later today, honestly. And then we have a webinar if you want to dig deeper into Cilium and what's happening there and what's coming with new releases. There's a webinar that's happening later today after our stream. Stay here with us. But
exactly.
There's a link to that webinar. And then I finally dropped a link to if you want to sign up for the Cilium newsletter. There's one of those.
And the webinar will be interesting, and it'll be recorded, so you can watch it anytime you want. But the webinar is basically Thomas Graf, our CTO, introducing all of the new functionality and capabilities in Cilium 114, which is our latest, which is one of our most recent shipped products at Observability.
Excellent. So I'm going to hop over behind the lightboard, and while I do that, I have a couple questions for you. One's a soft question, and one's a technical, like a community-related question. Two questions I have. One is, you mentioned tag and you mentioned working group. Like, what are the difference between those two things? Okay. And then the other question was more, last time you were on Enlightning, you said you were about to be in a Rubik's Cube tournament. So I'm also curious, like, how your Rubik's Cube tournament experience went.
All right. So I'll do the tag and working group one first. So tag and working group. So technical advisory group is a group of people that are brought together to be to form a technical advisory group. And the scope of that is fundamentally different from what we consider to be the scope of a working group. A working group is really focused on a specific task or a specific function or a specific focus for a finite period of time. We're going to spend 2 weeks. We're going to put out a couple of white papers. We're going to be doing, some particular research into a specific domain or an area. And then we're going to consider whether the working group should continue from that perspective, or whether that should, or whether the scope itself should be changed or adapted based on what we've learned from that experience. It is possible for a working group to become a tag. So to your point, like if we had like tag runtime and they had decided, you know what, we're going to put forth a working group that is focused on AI. We want to put a couple white papers that discuss how AI works together with open source projects, and we want to focus on that element of it, and that acts as a forcing function to gather the people in the AI community that would be focused on that particular domain. And then now you have that group, and you're like, hey, what do y'all think about being a technical advisory group? You can see how that would follow up basically up to the other. But generally speaking, it doesn't work the other way around. You wouldn't take a tag and turn it into a working group, because that would greatly limit their scope, as it were.
That's very helpful. Thank you.
The Rubik's Cube competition was fascinating. I went to the university here in Berkeley, and I went to like, kind of one of those big community buildings that was kind of near it. And there were maybe, 50, probably maybe like 60 or 70 people. I was clearly probably the oldest of the bunch, even the people who were organizing it, right? But it was still really fascinating because it's absolutely one of those events that I love. It's one of those events that you can feel that this event is one of those events where people, everyone is welcome. Doesn't matter if you've never cubed before. Like everyone is welcome to be here and be a part of this experience and have that. And I love that part, right? I mean, like that's one of those things I think we should, generally speaking, there should be more events like that in the world, And
Absolutely.
so
And I never heard the verb cubed before, and that was a joy just now. If you've never cubed before.
if you've never cubed before, yeah. And so I did okay. I had like the way that they do the thing. So if they were going to compete in the 3x3, which is what this puzzle is, right? Then what they do is you put your puzzle into a cup with a little tag that has your name on it. And that tag will also record your times. And so they bring that cup with the unscrambled cube over to a bunch of scramblers, professional scramblers.
Yeah.
and they scramble them and they don't just randomly scramble them. They actually have a set of instructions on how to scramble from a solved cube to the scrambled state.
So everyone who competes is starting from the same scrambled state.
Not from from a random scrambled state, but specifically to that scrambled state. So they actually have they scramble it to a random state, and they know that they have scrambled everybody's cube differently.
Okay, fascinating.
And then,
so is there an element of luck then that you got to scramble that's a little
to
faster
some degree,
to solve?
yes. Yeah.
Okay.
I mean, there are solves that move faster than other solves, and they account for this because you solve a puzzle 5 times, and they drop your low time and your high time, and they average the rest.
Oh, okay, got it.
Right. So your time when you leave the competition, your 3x3 puzzle time is actually is an average of the 3 medium times of your solves, which is really
okay. That's fascinating. And then it seems to have a lot to do with just like how fast you pick it up and put it down. Like there's an element of like reflex speed in addition to like thinking speed.
Very reflexive because it's very pattern matchy, right? So like you're doing a thing where you have to learn like a pattern to solve the puzzle, right? And that's usually what people refer to as like CFOP or cross first orient the top and permutate the top. And you then have to like fill in these first 2 layers, and then you orient the top all the same color, and then you permutate the top so that all the pieces are on the edges are in the right spots. So if you want to learn more about cubing, there are a number of really good YouTubers out there that teach it and do it.
I can see myself getting addicted to that, to a pattern matching. Yes, I could.
Yeah.
But I need to be careful because I'm obsessive, in a good way. Like I can rein it in for good, but I have to be careful.
I would say I'm definitely obsessed.
Yeah, I got you. We have let me see. I use this to let me just try to highlight comments. My iPad over here in the corner, and it's being a jerk. So I'm going to highlight a comment over here. Hello, hi Koromahaju, so happy to see you.
Welcome.
And also, hi Spirit. Yeah, it's hip to be. All right, let's just. Oh no, it's going to put me on the screen. There we go. Yeah, camera 2. We didn't want that. Okay, here we are, and I can highlight comments from over here. Great. Okay. So
here we are. Blank slate.
Here's blank slate. So I've been doing a series on service mesh, and this is part of that. Yep. Except that Cilium isn't just a service mesh. So these other service mesh projects I've been starting by asking, like, what is service mesh for every project? But you've told me that it might be better to start with Cilium to ask the question, what is eBPF?
Yes. And if you have seen that documentary, it's pretty clear why that is. It's been really interesting. So eBPF is a kernel technology.
I might ask some extra silly questions today because there's so much
I'm,
I don't know. But when
I'm
you
here for
say
it.
a kernel technology, you mean the Linux kernel, or is there some other possible meaning for that?
Well, interestingly enough, I do mean when I said it, I do mean the Linux kernel.
Uh-huh.
But eBPF is also being developed for the Windows, for Windows and, and
Oh.
other environments. So even though typically speaking, we think of eBPF as a Linux kernel technology, it's also being
Uh-huh.
made available in other environments, which is pretty exciting.
Cool. So it is okay. eBPF. Well, first, okay. eBPF is a kernel technology.
Mhm. And you can
Okay.
consider it in some ways. You can consider it to be like people have described it as the JavaScript for the Linux kernel
Ah, why?
because let's treat the if you think about the Linux kernel as just one big API.
Uh-huh.
And when you are in, and when you're running a process or doing literally anything that is
Uh-huh.
on a computer that has a Linux kernel running, everything that you do is probably tied to some sort of an API call. I'm going to go open a file. I'm going to open a network
Mm-hmm.
socket. I'm going to make a connection to the outside world. I'm going to manipulate the MTU size on a network interface. I'm going to do pretty much anything that you would do, change paths, change the file system, make a new file system. Like all of these things represent API calls to the Linux kernel in a variety of different ways.
Okay.
And what eBPF lets us do is pretty much anywhere across that entire API surface, we can catch the particular call that happens against that API server, and we can
Mm.
determine whether we want to just gather context about what happened or whether we want to
Mm-hmm.
manipulate what's happening.
Oh, that's that's very powerful.
It's
That's
incredibly powerful. Yeah. And
yeah.
and and I think I can kind of see you intuiting one of the obvious next questions, which is like, how is this safe?
Yeah, that's exactly what I was thinking. Whoa, you just read my mind. Like,
Because as soon
yeah.
as I describe that to anybody, most people are like, but why would you want that? Right? Like that seems like
Yeah.
yeah.
Yeah. So, I guess you're going to get there. But in the very short term, let's finish our definition where eBPF is a kernel technology.
Yeah. It is
What?
a so and how do I want to describe this in a sentence? I would say that it yeah, so can we say that this enables us to inspect and manipulate any call to the Linux kernel?
Love it. What does eBPF stand for?
Extended Berkeley Packet Filter.
Berkeley
And the
again.
and the documentary gets into what that means because it's been a really interesting road for eBPF. Like initially, BPF, which is before the extension, existed in the Linux kernel for some time. And the extended Berkeley packet filter is now, and BPF was more focused on specifically around things like networking components and those sorts of bits. And when the extended Berkeley packet filter came along, it was like, what if we could do a lot of the same functionality, but across the entire kernel, enabling us to change the behavior of your kernel or change the behavior of the way that of particular Linux functions and how they operate. Pretty exciting.
So it's very exciting. And so how is it not as dangerous as it is advantageous?
So there are a couple of different ways that this is actually made safe. One of the ways that it's
Uh-huh.
made safe is that, and you can consider an eBPF program, and that eBPF program is like an event-driven program. And this means that, like, whenever any process within the system writes
Mm-hmm.
or opens a new network socket, that process that it will hit that program that's basically injected into that API, and it will trigger whatever that program is. Now let's just take an example. I want to look at every time somebody opens a new network socket, and I want to determine what the destination of that traffic is. And based on a list of IP addresses that I trust, I want to allow that connection to continue. And if it is not one of those IP addresses that I trust, I want to drop that connection or manipulate that connection so that it will be dropped at the Linux kernel. So I write the eBPF code to actually do this, including the list of IP addresses that I trust. And before I can put it in the Linux kernel, the program that I've written has to be statically analyzed by the eBPF verifier to determine, one, that it's not an endless loop, two, that the instruction set is clearly laid out and that it understands exactly what, and that it understands that it's a finite request that has a beginning and an end, and it's not going to crash. That it can actually successfully run it and be safe about it. All of these things have to happen before that code ever gets injected into the kernel around that particular function. And the eBPF verifier can be really, like, as you think about more complex things to do with eBPF, the verifier can really be a chore. It can be a lot of work to get past the verifier.
And then what's the second thing? It's not an endless loop, and what else?
And that there's like a clear set of instructions that like has a beginning and an end that will not crash the kernel. So there's static analysis on it to make sure that so that the program will not crash.
Okay. Is that accurate, just to put the program will not crash?
Sure. Or that the code is safe. Let's just put it that way.
Okay.
And this happens before any program is put into the kernel. It's true of every time. Like, even if you're injecting the same program, it would still have to go back through that process.
So, talk to me about the language of like getting injected into the kernel. What does that mean?
So when we say that, so eBPF is a language that allows us to write kernel functions that will run natively in the kernel, which means that this little code bit that we've this is why it's compared to JavaScript, right? So JavaScript is like a function that is written and shipped with your and shipped with your web page, and then operates basically in the browser's kernel.
Okay.
It's the same mechanism effectively with eBPF. When you write this program and you determine where in the stack you want to associate this program, the kernel is now operating that code function directly whenever any event that matches that particular program's focus happens. So if we were watching for network sockets to be opened and we were watching for what the destination of that particular traffic is, then anytime, any program, anywhere in the Linux in the entire operating system, whether within a container or whether on the underlying host, anytime a socket was opened, we would evaluate that particular connection to determine, do we have to do work or not do work? And we would do that at the kernel layer, just like the kernel was responding to that API call. I saw a socket open. I had this eBPF program. The result of this eBPF program determines what I do next.
Fascinating. How recently was this technology developed?
It's been a little bit. It's been like, I don't know, I think 7 or 8 years now at this point.
Okay.
Maybe a little longer.
So, let me think. So, shortly after Kubernetes.
Yeah. And it's been around quite a bit. And what's interesting about Isovalent as a company and Cilium as a project is that you could say that the first few years of the company were us focused on basically bringing eBPF to the place where it could be leveraged to build a product like Cilium.
Yeah.
initially it was not ready for that. And there are a number of other things in the eBPF space which are useful, like eBPF helpers, which are like, you can consider them to be functions that you can call when you're writing eBPF code. And these eBPF helpers are like, the kind of the language primitives that you might be able to use that describe kind of an easier way to do a particular thing, like a dictionary or a lookup, or like these sorts of things. And so these helpers are things that we've changed over time quite a lot, right? Like, we've added more of these. We've enabled more capability within the Linux kernel to understand how different components within the Linux kernel are operating. These helpers also help us determine context, like when a particular system call happens, the context that happens around it might be related to a different previous system call that was, and how do we actually gather the context correctly for all of it?
That makes a lot of sense.
Yeah, and so Cilium, in its way, like, has been kind of on that journey. A lot of the folks that I work with at iSurveillance have been and continue to be dedicated to extending eBPF in the technology in the kernel for everyone, and then leveraging that extension or that capability, those new capabilities, those new functions in the products that we're developing.
Super cool. Okay, so we have eBPF, and it's going to help us with Cilium. It's an important. So now that we've said what is eBPF, can we say what is Cilium?
Yes.
Excellent. Okay. What is Cilium?
So Cilium is primarily a networking product.
Oh. So it's not service mesh first, it's a networking product first.
Yes, exactly.
Interesting. Okay.
And I say
Can
that.
I say networking technology instead of product?
Yeah, you could totally say networking technology. That's a great choice. And I say that because Cilium is focused on solving things like CNI, which is the container networking interface. It's focused on solving connectivity between pods and other pods. It's also focused on solving connectivity between clusters. It's focused on solving connectivity between nodes. It's focused on solving connectivity in cloud environments and in legacy environments. Maybe we should write that part. Cilium is focused on solving connectivity and security and observability in cloud and physical and legacy environments. Networking, security, and observability.
Networking, security, and these three points, I will say, have come up in every single service mesh talk.
Absolutely, yes. And they and for good reason. It's really interesting that, like, there have been actually a number of really great talks put out by a number of people, including one by Tim Hawken, which I really liked, that was called "What a Fine Mesh We've Created," which which highlights exactly that, right? Like, when we are trying to solve networking for a container orchestration like Kubernetes, then, like, there are a lot of different people that come to this with different requirements, right? In the talk that you and I did earlier around the Kubernetes networking model, that was where we basically constrained the set of requirements specifically to the Kubernetes networking model. Like, what requirements are necessary to be a CNI? Like, what does it mean to have a CNI solve those problems? And what are the constraints? What are the problems that we're trying to solve, right? And so that's stuff like pod-to-pod networking, pod-to-pod network isolation, being able to define services within your Kubernetes cluster so that you don't have to rely on ephemeral IP addresses. You can rely on the service abstraction. Being able to ensure that the underlying host can do health checks against the pods that are running on the host itself, making sure that all pods are able to define connectivity between each other. There's all of these constraints that fit into the CNI bucket.
Okay.
And so you're absolutely going to have people like when you're talking about service mesh, it's going to be a similar set of questions. I want to know, like, I want to be able to ensure that pod to pod traffic is going to be secure. But we're going to get into service mesh here in a minute. First, let's finish the CNI piece. All right.
Okay. I forget, you said in cloud and what environments?
In cloud and legacy environments.
Cool. Do you feel that like this is a good definition of Cilium? Okay.
Yeah.
I like the word connectivity instead of, or at least in addition to, networking. Networking like has some sort of already preconceived notion about like, or maybe but like connectivity is like more accessible somehow. I don't know what it is, but I like when you said connectivity. I think I already have like maybe a bad impression that networking is hard. And then when you say connectivity, I don't have that idea that it's hard yet.
I have a new thing for you to associate in your brain with networking, which has always brought me kind of a little bit of chaotic joy, which is that like it's this meme of the most interesting person in the world, you know, and it says, "I don't always find root cause, and when I don't, I blame the network." So whenever I mean, it's like, it's funny because it's also generally true, right? People, when they can't find a reason why things aren't working correctly, then it must be the network that's doing it. So yeah, most people think of the network as very opaque or very hard to understand or very difficult to, and that's actually one of the powers of Cilium.
Yeah.
Because this is actually where the observability piece ties in.
Okay.
So
yeah.
Let's talk about how Cilium does its thing.
Okay.
And to do this, we're going to jump back into the CNI realm for just a minute, and we're going to kind of build our way up into service mesh.
Okay. Is this best for diagrams or words?
I think it's going to be words.
Okay.
Yeah, I would say I think this is going to be words. So when you, I'm trying to think it through, like, how would this actually be better displayed? Like
Basket Case says it's always DNS.
It is always DNS. Yeah.
That's a good one to blame too. Absolutely. Yeah.
That's another good one. So when a new pod is created, that new pod, when the kubelet is actually trying to realize that pod, part of the work that it does is calling out to the CNI. And we talked about this in our CNI discussion, right? So the kubelet says to the CNI, in this case Cilium, here is a new pod. I need a networking stack for this new pod.
Okay. And what does a networking stack mean? I know it's an IP address. What else is it?
It means an IP address. It usually means what's called a VETH pair or a virtual Ethernet pair. One, which is like a little networking pipe, where you put packets in one side, they come out the other side. You put packets on the other side, they come out the first side, etc.
Okay, nice.
And then in this VETH pair, they'll have one side of the pair in the underlying host's network interface or TCP/IP stack, and then they'll have the other one dedicated inside of the network, inside of the container's networking stack. And that's why when you're inside of your pod and you do IP adder or you do any of the commands to show networking stuff, you only see one IP address. You don't see all of the other interfaces.
Cool.
Right.
So
when that, go ahead.
I was just going to bring you back to where you were in the story, but you got it.
Oh, so when that happens, when the kubelet actually requests that from us, what we do is we actually provide that, right? We make a VETH pair. We put one inside the container. We have one out in the namespace. And then we also do a thing where we generate an identity for that particular pod. And that identity is unique to the pod. And that identity and the generation of that identity, and actually is the beginning of where we start applying eBPF to this particular pod. And that means that we are going to insert those eBPF programs. Go ahead.
I have questions. One is, how is the identity like an IP address is an identity? Is that not good because it could be reused within the cluster? Okay.
Exactly.
And
yeah.
then my second question is like, should I be capturing this? And if so, is maybe a series of steps the best way to do so?
Yeah, I think a series of steps is the best way to do so.
Okay. So I'm going to make you back up on me and say, what is step one?
Kubelet Kubelet
Yeah.
is creating a pod.
Okay. And then step two, Kubelet reaches out to CNI.
Which in our case is Cilium. Yep.
Okay.
It says, give me a networking stack for this pod.
I like when they have personalities and say things.
Yeah.
Give me a networking. Okay.
And Cilium does that.
Okay.
And it also generates an identity for this pod.
So the whole pipe thing, the V pair, did you call it? And the IP address, that's not really too relevant.
I think we talked about that in the CNI piece of it. I don't want to dig too much into that here.
Okay. And it's Fuel Snobble's here. Hello, Fuel Snobble. Thanks for coming, friend. Hello.
That's a great name, Fuel Snubble. I like that.
And it also gives the pod an identity. Generates?
Yep. Generates an identity.
Okay. For the pod.
You could say gives. Either way works.
Okay. For the pod.
Yeah. And attaches an eBPF program.
Oh. Okay.
For the pod also.
And it attaches this eBPF program to the pod. Does that mean it's like? Oh yeah.
To the network namespace of the pod, we'll say.
Okay. Okay, got it. So now when we're talking about a network namespace, we're talking about like a host level, like a host machine abstraction, right?
Not quite. Yeah. So network namespaces are the virtual abstraction in the Linux kernel that allows us to create multiple network stacks, right? So when I say like when you have when you're in that pod and you do IP adder and you see only one IP address, that's because you're in your own private networking Idaho, right? Like you have your own little networking world with your own loopback address and your own IP address and your own network interfaces.
Okay.
And that's separate from the networking stack of the underlying host.
Okay.
Right. And that's where the namespace term comes in, because the way that we describe these individual components that actually relate but are not the same is by namespacing them. Okay.
Is there a network namespace at the container level?
Yes. And so in this case, I would remove the word host because we attach that eBPF program to the containers networking namespace.
Oh, it's not the pod's networking namespace. It's a containers networking namespace.
Well, it would be the pod's networking namespace, but where you've written attaches an eBPF program to the host network namespace, the host part isn't actually relevant. I would say pod network namespace.
Awesome. I love this. Cool.
Because that's the crazy part about it is that like the pod has a network namespace and the host has a network namespace.
And the container has a network namespace.
Yeah.
I'm learning.
And the interesting thing about a pod is that network namespace is shared across all of the different containers within that pod.
Yes.
Okay. So this eBPF program that Cilium associates, let me just talk through this real quick before we capture it.
Okay.
This now that we have an eBPF program associated with this, we
Uh-huh.
have effectively solved the observability problem, which is really interesting.
Yeah. That's a
Because
big
now,
statement. Yeah.
because now what we're doing is we've actually implemented in this eBPF program a mechanism by which
Mm-hmm.
we can report on anything that happens within the networking namespace of this pod. So any new connections that happen, any new packets that are being forwarded, anything that happens from that network namespace. When you do Hubble Observe, and we're going to talk about Hubble here in a second, you're going to be able to see all of those things happening as an event stream. So one of the first thing this eBPF program does is start generating events, network events that happen whenever there is a network connection. We start generating an event stream.
I want to write observability is solved because that is
Yes.
big.
Yeah. So the first thing we do with that eBPF program is we start generating events related to networking within that network namespace.
In the pod network namespace.
That's correct.
So it's generating all of the events that happen in the pod network namespace.
Yeah. And this is just us observing what's happening in that network space. Now that we have the eBPF program in place, we can say anytime anything happens at that networking layer, we want to be able to generate an event about that, right? And that event can be this pod tried to talk to that pod. And that event can be this pod tried to talk to this fully qualified domain name, tried to talk to google.com. This pod tried to reach outside the cluster. Any of these events are things that we can capture.
Okay. So,
Now,
cool.
Yeah.
So this isn't happening at the container level. This is at a pod level. So
this is happening at the kernel layer, right? So like this eBPF program is injected, and now anything that happens within the processes associated with that pod, anytime any of those processes within that pod tries to open a new network socket, anytime it tries to make a connection to another pod, anytime it tries to make any kind of networking activity at all, right? We now have something that will intercept that new connection and be able to pull context out of it so that it can so that events can be generated about it.
Okay. Cool.
Now the next part. So in the CNI, the next thing we do is the network policy.
Network policy, which we talked about in the Kubernetes network episode. A network policy is made to restrict access. Like by default, every pod should be able to talk to every single other pod in the whole Kubernetes cluster. So network policies are put in place to restrict access between pods. You don't want to be able to talk to one another. Also, hello, Findle. I'm glad you're here. Cool.
And another good reason why that happens is because, you as a platform engineer or a security engineer, you have an understanding of what is normal network traffic back and forth between applications. And this is a big assumption that a lot of people make, right? But let's just say, for example, that you do actually have that information. And the reason that's useful to you is because you want to be able to identify when traffic is happening that shouldn't happen. Because when traffic is happening that shouldn't happen, perhaps that means somebody's trying to attack your system. They're trying to laterally move between different networks or between different components within the stack. And the network is an area where we can actually harden things. And we can say, no, normal traffic looks like this. which means that you can only do these things. And if you try to do something outside of those things, not only will it not work, but I'll also be notified that you did it. Right? So I can say, okay, well, why did this application try to make a connection to this database? It's a web server. Why is the web server trying to talk to the database? Right? And then we can determine, is this the right thing or the wrong thing? Should we write network policy that allows it, or should we continue to not allow that?
And so how does the network policy fit into our story right now?
So network policy is the next thing that we do with eBPF, interestingly enough. So when people write network policy that affects pods, we actually implement that network policy in eBPF.
Oh. And this is unique to Cilium?
Yes. Most implementations of network policy are related to IP tables, which is another technology that has been around for a long time in Linux and does affect the kernel, but IP tables was written kind of really with the idea that you would write it once and not really mess with it. And we have really abused IP tables a lot in the last, say, 10 years.
So it's happening. So network policy then is happening. So now that I know there's so many networks happening, is that happening at the host network level or the pod network level?
With IP tables, it happens at the host layer. With eBPF, it happens at the kernel layer. So it's above all of that.
Okay.
But we are implementing it against the network namespace that the pod is in.
Okay, and that's similar to what's happening here.
Yes, and in fact, it is the same as what's happening here. Yeah.
Okay.
Just like we can emit events, we can also extend that same eBPF program to do network policy.
Okay, so this is the same program.
Yeah.
Okay.
So this enables us to handle network policy natively at a native kernel speed within the Linux kernel.
Sorry, I'm a little behind. Okay, so so this is like this, when you say this is like the security level of what you're doing, right?
Exactly, yeah.
And what does it do more specifically?
So it's going to look, now that we have network policy applied, right? We're going to say, we're going to evaluate that network policy for every packet that moves through that stack. Because remember, this is event driven. So this is actually really interesting because it changes the way that people perceive how this stuff works. And I'm trying to figure out a concise way to describe it. But if within IP tables and most firewall implementations, there's this thing that is that's called allow established. And allow established means that even if I change a rule set, as long as the traffic was allowed at some point, then all of the rest of the traffic associated with that session will continue to operate. So even though I might say, I don't want anybody to be able to talk to this IP address, if at some point this application was allowed to talk to that IP address, and then we implement a new rule that says, stop that. Allow established will continue to allow that connection to operate until that connection dies.
Okay. Got it.
No new connection will be allowed, but any existing connection. Yeah. So allow existing is a really interesting security hole because it means that like as long as there's an existing connection, that existing connection will continue happily on until such time as it terminates.
So this is superior because it's happening as the events happen instead of needing a reboot on whatever connection it is to take effect.
Exactly. eBPF doesn't consider the session; it considers the packet.
Okay.
Right. So every individual packet is going, every individual networking event is affected by an eBPF program. Every packet is affected by that eBPF program. If that program changes, the very next packet is affected by that program.
Yeah. That makes sense. You're teaching me the problem and the solution all wrapped up in one.
Nice.
Considers packets, not session. Cool. We have Keel Snobble cracking jokes like you do. For each IP packet, can we send it to ChatGPT? Does it look suspicious? Let's do it. Only one way to find out. All right, so now my guess is, we talked about security and observability, so now we're going to talk about this in a networking context. Oh, are you there, Duffie?
Yes, I'm here. So when we talk about, so this is now we're getting the security piece, and this security piece enables us to implement things like network policy for every event that is generated. Exactly. Which in my opinion, it's like my good friend Christopher, he describes this as, so you don't have to wait for somebody to finish stealing the stuff. You can actually stop them. Right?
Yes.
Which is a very interesting way of putting it.
And I've done I've done a series on policy, and so I talked to OPA and Caverno, and also a technology called Cube Armor that implements policy at the kernel level using LSM and eBPF.
Nice. That's awesome.
Yeah. Mm-hmm.
I mean, and if you think about it, like if you're implementing these things at the kernel layer, you're as close to the source of this traffic as you can possibly be, which means that you're able to do things like, you could actually you could make a decision about whether to allow or deny this traffic at the point where the socket is opened. Which means that like you're affecting the traffic before it's even a packet.
That's so historically with the other kind of policy tools, you can't it would take a ton of compute to be able to implement policy in that kind of fine-grained way.
Well, what's interesting is that, and this is actually why allow established works, for example, or why it's been created. So allow established is actually created originally because it does actually mean that or what it's trying to solve for is there are a number of different sessions that are open at a given time. And as we build more and more containers and more networking namespaces and more connections between different applications, you can imagine that every one of those things has to go through and be evaluated by the rules of IP tables. So how can we greatly reduce the evaluation of all of these things, right? We could reduce it by saying, let's create an allow established rule. Once I've made the decision about whether to allow this session or not allow this session, then that decision should remain true the entire length of the session. And that means that all of the packets that move back and forth between my browser session and this active session that I'm connecting to, right? All of them should be allowed, not just one of them, not just the first one. And that reduces the weight of the compute weight. So it reduces the amount of time that we spend inspecting all of these packets. With eBPF, because we're able to do this at native kernel speed, we don't have that problem. Right, we can actually do this very quickly, like at native kernel speed for every event. We already have processes within the Linux kernel to actually manage all of these individual events, and so this is actually just extending the process in the Linux kernel to handle a decision about whether to allow or deny this traffic at that same rate of speed. So it's very fast.
Is it near native? Usually.
No. It is
actual native?
Native kernel speed, yeah.
Dang. That's like superhero stuff.
It is superhero stuff.
Why is it so fast?
Because what we're doing is we're taking the fastest part of the path, the stuff that happens in the kernel, and we're just making it do a little extra work.
Okay.
Right?
It's not
So
moving
instead
it
of
around
actually... Exactly. Yeah. So instead of
Yeah.
taking the traffic, moving it down to a different section of the kernel, moving it to up to another section of the kernel, moving it down into user space, moving it up and like making decisions at different points of that whole process, we're saying, you know what? Let's just make all the decisions like right at the top.
Right where it's happening. Yeah.
Yeah. Right. Which allows us to cut a lot of the going back and forth out of the picture. Which is
Makes
wild.
sense.
Yeah. So that brings us to the next thing that eBPF does, which is or the next thing we can do
Networking.
with this. Yeah. Networking.
All right.
So say we have two pods on the same host. Or say, yeah, so we have two pods on the same host.
Okay.
And there's going to be traffic going back and forth between the two pods that are on the same host.
Yep.
Now, typically what that would mean is that the connection from the packet from the one pod would have to go from the kernel, like down into user space through IP tables to determine any network policies that would be applied, and then eventually up into the next network namespace where the other pod resides, and then the other pod would receive the message, and it would have to go back through that whole process back up to the other pod. And you can imagine all of these individual steps actually add up quite a lot of latency between pods, even on the same host.
Okay. Yeah.
With eBPF, we can actually shortcut that traffic, which means that because we're at the kernel layer and we understand the connections between the two sockets. We understand these two sockets are actually just trying to talk to each other. Why don't we just allow them to communicate with each other directly based on network policy, of course. So we can do socket layer load balancing is what this is called.
Socket. Okay. So in order to really understand that, it's like you have to understand what problem it's solving, which is
so if we write two boxes.
Oh, draw it. We're gonna draw it. Okay.
I think this one is a diagram, yeah.
Sure, let's do it. So we have two pods that want to talk to each other.
Yes.
A pod and a pod.
And they're on the same host.
Okay. And then I think in this case we're gonna make the host look like this.
Oh, I like it.
Yeah.
Now let's put another box in between them that's called IP tables.
Pod. They have to go through the IP tables to get to the host?
And to the other pod, both.
So it's kind of like this. Oops, I'm not very steady-handed. So this is the IP tables, and then this is the host. Does that make sense?
I think that the yellow thing that I see on the box, because I think there's some border cutting off the bottom half of this. The pink one isn't showing up.
Oh, yeah. Dang it. Shoot.
So, but it's okay, though, because the yellow one should be the host. And there should be like a blue one in between the two pods that is IP tables.
Okay. IP tables. And then this is the host.
Exactly.
Okay.
And so now when a connection is moving back and forth between these two pods in a normal CNI, this connection is actually going to have to go through IP tables, and it means it's going to have to go from the kernel to IP tables, back to the kernel to the pod, and it has to go back and forth quite a lot.
So it actually goes kernel, IP tables, kernel, pod.
Yeah.
Okay. And then instead,
what we do with Cilium is we just allow those two pods. We can make a drawing, another line that goes back and forth between the pods themselves, and it goes directly between them. No IP tables.
Cool.
I love Taniwa's idea.
Oh, Taniwa, welcome. Yeah, we need, yeah. And actually, maybe we can let people angrily flip the
Yes.
tables. Yeah.
Yes. That'll be the eBPF people who are like, boop. Yeah. Yeah, I love it.
And Tanawa says people could be the packets, and it could be a learning exercise. You have to, if you want to talk to another person who's also at the table, you need to talk to the table, the floor first.
Yeah. I've also seen IP tables represented as like a bouncer, in front of a busy club, and he's like and the bouncer's trying to like figure out like, do I allow you in? Do I not allow you in? But then once you're in, you can be like, you have in and out privileges.
So pod, host, IP table. Host.
Perimeter defense.
Pod.
Which I like nightclub defense model instead of the ones that people usually refer to, which is the anthill. Nightclub,
yeah.
Nightclub is a bit more evocative than an anthill, which is usually how people describe the perimeter defense model.
Okay, got it. Is this related to a perimeter defense model?
No, in this case, it's called microsegmentation. So this is more like,
okay,
how do we secure things back and forth between two individuals? Perimeter defense is like, I have a data center, and inside of the data center are lots of juicy applications that do all kinds of interesting things with data. And when my perimeter defense is, do I allow you into that data center at all, or do I not? Right? And perimeter defense, once you're inside there, well, now you're inside. Now you're next to all of these interesting databases and all of this other super valuable data. Like, how do I make it so that each individual component of those do not allow you or do allow you in? And that's microsegmentation. That's where things like network policy come in.
Got it. That makes sense. And Tanawa says an anthill is zero trust, where every ant is constantly checking the membership of other ants. Is that how ants roll? I'm not that intimate with ants.
That is definitely not how ants roll. That'd be cool though if they did.
All right. Cool.
All right. So that's one of the things that we can do from the networking perspective. We can also excuse me.
Mm-hmm.
So we can also, and this is actually one of the coolest features, like that people are attracted to Cilium for.
Mm-hmm.
We can do kube proxy replacement. That'll be the next thing at the top, I think, probably.
Yeah. So this is, we'll call it 7. It's also related to networking.
Yep.
Okay. Kube proxy replacement.
Kube proxy replacement. This represents a lot of really cool work with eBPF.
Cool. So kube proxy generally is a process that runs on every machine, and it helps facilitate the connections that need to happen between the machines.
Yeah, and it's basically it implements an abstraction within Kubernetes called services.
Okay, and we talked about that during the cluster IP and node port and load balancing services specifically during the last one. Cool.
Yep. And so, typically speaking, the implementation of kube proxy is also in, believe it or not, IP tables.
Oh. Okay.
So this is actually something that we have implemented directly in eBPF.
Oh, okay. So So can we say what kubeproxy is real quick?
Yeah. So kubeproxy is a Kubernetes component.
It's native to Kubernetes, right?
Yes, exactly. It ships with the Kubernetes binaries. It is a native Kubernetes binary.
Okay. Okay. That.
Implements services like node port and cluster IP.
Okay. With using IP tables.
Typically leveraging IP tables, sometimes implemented with IPBS. So you could say IP tables or IPBS.
IPVS.
And IPBS, and for your part of it, means IP virtual server, which is another kernel technology that allows you to basically create like a load balancing set of primitives in the Linux kernel itself, which is pretty interesting. Kernel load balancing mechanism.
So this is a question I've been hanging on to since even before the episode, and now it's maybe time. I've heard that Cilium is now a part of the Kubernetes installation provided by all major cloud providers.
It is actually it is widely available, I would say. So you can actually use Cilium as your CNI in every cloud environment.
And so is this part of that, or using this kubeproxy instead of the installation that's native to the Kubernetes?
So with kubeproxy replacement, you have to have some way of understanding that kubeproxy won't be running on the cluster. And in some cases, you don't really have that choice. But in some cases, you do, right? So like kubeproxy replacement, I think, is probably most useful in like highly scalable environments where you have a lot more, where you kind of need to have more control over what's happening or how you've built the stack, I should say. So kubeproxy replacement is useful in high scale environments where you have more control over how you've built your Kubernetes stack.
Okay. Is useful in high scale environments? Is that what you said?
Yep, exactly. Yeah.
And why is that?
Because again, it's the same reason that all of the other stuff in eBPF works really well. We're making these decisions basically right at the connection up, right at the socket, right? So when you try to interact with a service of cluster IP, you know how in the way that it would normally work is the packet would find its way down to IP tables on the host. Kubeproxy would configure IP tables on the host. The connection would actually hit a particular line in IP tables that would disperse it randomly across a set of healthy endpoints, and kubeproxy would be making the decision basically at that point about how to manipulate this packet so that it would go toward a healthy pod instead of going toward a service IP. And we do all of that, including the natting, in eBPF.
And why is it especially useful in high scale environments?
Well, previously I had said that one of the challenges of IP tables is that when the original design of IP tables came around, the idea was that you would write a bunch of rules to secure a given host, and that those rules would not change. And an artifact of that is that IP tables is not what you would consider to be atomic, which means that when you make a rule change, any rule change, the entire rule set has to be reloaded in the kernel.
Okay.
Right. So you can't like say, oh, I forgot, I just wanted to change this one rule, because you're not changing that one rule. You're changing your IP table set might comprise of like 1,000 rules or 2,000 rules or 3,000 rules, depending on how many rules it takes to actually solve the problem that you're trying to solve. And any change to any of those rules represents a complete reload of all of the rule set. So,
On every single node.
yeah. Well, no, on the node that we're talking to, right?
Oh, okay.
But yes, in your case, like if kubeproxy were to create a new service,
Yeah.
that new service is represented on every node, and all of the
Uh-huh.
nodes have to then basically reload all of that thing. So you're right; it's a distributed system, and when you make that change, you make that change to everybody.
Yeah.
So this represents a something of a landmine in kubeproxy, which is overall working okay, but has the
Uh-huh.
same set of challenges, right? Like if we're implementing things like network policy in IP tables, and we're implementing
Uh-huh.
things like kubeproxy in IP tables, and we're implementing things like node ports in IP tables, and there's a lot of change and churn in IP tables that is happening all the time.
Mm-hmm. Taniwa has some good comments. Taniwa says kubeproxy is one of the oldest components in Kubernetes too, which is
It is, yeah.
fascinating. And IP tables would reload every 5 seconds because of load balancing too. It was terrible.
Yeah. So the benefit of moving all of this up into eBPF is now it is atomic. And now we can be a lot faster about when we make that decision. So before the packet even hits user space, the natting has already happened. The decision has already happened about what to do with this packet.
With kubeproxy
replacement.
Well, I was going to say with kubeproxy, the IP tables were constantly changing.
Yes.
Constantly reloading, changing and reloading, updating and reloading.
And IP tables was never meant to be used at in high churn environments.
And that made it slow, which was slow.
I think it's actually pretty fast. The problem is not necessarily that it isn't quick. The problem is a problem of convergence, right? So
okay,
IP tables makes the decision that it makes pretty quickly. The problem is that we're constantly pulling the rug out from underneath it.
Okay.
Right? Like we're saying, make this decision based on this incredible stack of rules. And IP tables is actually pretty quick at that, But then we say, but wait, one more rule. You have to read the whole rule set again and make, oh, wait, hold on, there's one more rule. And then you have to so we're constantly pulling the rug out from underneath IP tables and assuming that it's going to be fast enough to make this decision, which is pretty wild when you think about it.
So it made the system slow to converge, if it ever really converged. Yeah. Cool.
I mean, it does actually manage to converge very quickly. It's I will say, as much as I talk about IP tables as a challenge, I am impressed. I am honestly impressed with how well it manages in this environment. I mean, like it's like we are asking a lot of IP tables when we talk about things like container orchestration systems like Kubernetes, and somehow it manages to actually stay on its legs. And I don't know how that's possible. Like it's mind blowing.
If I have a large system that's using kubeproxy and I switch to Cilium for the kubeproxy behavior, what changes would I expect to see?
So you would see no convergence time. It would just immediately start working faster, and you would see a lower amount of CPU because the amount of work that kubeproxy is doing would drop. It wouldn't be doing any of the connection stuff. So benefits are CPU, and also convergence time would be faster, and also eBPF is atomic. Which means you can make a change to one.
Low convergence time or node convergence time?
I would say actually no convergence time.
I still didn't understand which word you said.
Zero convergence time.
Ah, 0. Cool. And then what's it the rules are atomic instead of
Yes.
being associated with each other.
Yeah.
Networking rules.
So when I make a change to when I add a new service in eBPF, with eBPF replacing kubeproxy, all I'm doing is basically just implementing a change in a map. I'm not actually, which means I can just inject it. I don't have to tear the whole thing down and make a new change. I can just inject the new line in the map.
I hear you Rubik's cubing. I love it.
Oh,
yes.
My fidget cube.
Peel Snubble has a great idea, which is just to allow every connection. That's how you can be super fast.
That's very true. I mean,
yeah.
It's the quickest. Yeah. Security versus convenience.
What am I? DNS is older than the modern internet. That's
wow. DNS is older than the modern internet. I guess that depends on how you're describing at what point did we become the modern internet?
yeah, I guess. Yeah. That's a great question. Is it Flash?
Right? is it Flash? Wow. That's beautiful. No, it's true. And actually, you know what's wild is I there's actually a thing that I want to share with you, which actually also kind of blows my mind, which is, I think, perhaps the first implementation of DNS. So before DNS is basically domain name lookup, right? So the idea would be, if I want to go to google.com, somebody has to answer the phone or somebody has to give me an idea of how to go about that. That's DNS's job. So before that, no kidding, there was actually a book that was printed like a phone book. And this book was printed that described where all of the computer systems in a particular area are and what the telephone numbers were to reach them.
Whoa.
And it was a hard-covered book. There's literally a list of computing systems that are available at different universities. This exists.
Wow.
That was the first DNS. I have had my hands on this book. It is a thing that exists.
I hope
blows my mind.
Yeah.
Right? Like that was a thing that existed. Yes, absolutely. Timeshare systems. And yeah. But now that we're done talking about dinosaurs, let's get back to the fun stuff.
Awesome.
All right. So we have talked about observability. We've talked a bit about security. We've talked about networking. Let's talk about what happens between our stack and outside of our clusters, because that's where we can even do cooler stuff.
Outside of the cluster. Whoa.
Sorry, I'm adjusting my exposure because it's like the sun is like baking me. There we go. That's better. All right.
Taniwa also owned a Yellow Pages book of websites that had every registered address listed.
Because we humans have learned long before the internet how to print all of this stuff. And so
I remember phone books very well. It seems like the same idea. Like I could see how humans jumped from one thing to another.
Yeah, exactly. We already know how to do it. It's relevant. We want to have a list of places, a list of things we know about. So let's make one.
So this how Cilium does its thing, 7 steps, is really how it does its thing within Kubernetes, right?
Yes. Yeah.
And now we're going to talk about how Cilium does its thing outside of Kubernetes. Is that accurate?
We're going to talk about how Cilium does its thing in relation to. Actually, before we go into that space, give me one moment. Let me think about whether I want to jump into this or when I want to jump into service mesh.
Oh yeah.
So let's just put a piece right underneath this that says like number 8, and we'll say that Cilium also has a lot of capabilities. We can handle things like load balancing.
Mm-hmm.
BGP,
I
SRv6.
don't know.
Yeah.
I don't know what you're saying. Load
But I'm
balancing,
gonna
I understand.
yeah.
Okay.
So BGP is a way of announcing pod IPs and that sort of stuff.
BDP announces pod IPs.
Border Gateway Protocol, BGP.
BGP.
Yeah. And this is a thing. This is a thing that exists in like those legacy environments I was talking about.
Border Gateway
Protocol.
Protocol. And it exists in legacy systems?
Yeah, or data centers. You could say exists in data centers, and that would be good.
So BGP announces IPs in data centers. Is that correct?
Yeah, correct. That's what we use it for. It's not the only thing it does, but that's certainly BGP. Weirdly enough, all of the packets, even just connecting our video to each other at the moment, are going between are being routed between routers across the United States, between California and Texas, and how those routers know about each other. BGP. Border Gateway.
BGP.
Yes.
Oh. Okay, and then IPv6, I know about that, which is right now most of the internet is IPv4, but
Correct,
we're running out of IPs, so we need and IPv5 sucks. And so now we're on IPv6,
Yes.
which is a new way to do IP addresses where you could have more of them. But
Yes.
also they can be difficult to work with because a lot of stuff is not compatible. We have Dominico's here. Hello. I remember when there was a misconfiguration or a problem with the big BGP and half the internet went down. Wild. Yeah. Wild.
Definitely don't want to stare too long at the abyss that is BGP in the world today. But anyway. Yes. So these are all things that Cilium can do to improve connectivity between your Kubernetes cluster and your legacy environments.
Mm.
We should also write egress gateway in there. And we could talk about egress gateway a little bit, but we'll just put a side note on it or something.
Improves connect. Yeah.
Between your Kubernetes cluster and the rest of the world.
Kubernetes clusters and the world.
All right. Now, service mesh. Ha ha ha.
CILIUM. Am I running out of room for all the good stuff you have to tell me?
No, this is why I wanted to wrap it up on the networking stuff and open this up to service mesh. I think we're in good shape.
Cool. All right.
So exciting.
Yes.
So far we've talked about so many things. We talked about eBPF, we've talked about networking, we talked about security and observability, and we've talked about how observability helps us understand everything that's happening at the network layer. One thing I do want to point out, or I want to add to this real quick, is that observability piece is actually kind of mind-blowing, because it means that anywhere we have an eBPF program, we can gather context about what's happening and then present it to you so that you can troubleshoot and understand what's happening in the network. The network is no longer opaque. Right? The network becomes
that is pretty cool. Yeah.
And it's a mind-blowing difference, right? Like when you're used to the idea that networking is hard to understand and it's opaque and it's a thing that happens, but it happens below your abstraction. But then suddenly you're able to see, oh, here's the DNS request I made. And look, I'm getting DNS failures, right? Being able to see that stuff is mind-blowing.
It's I love that you say that because I'm new enough here that sometimes I don't understand the gravity of a thing.
Yeah.
And
But you,
so
but,
thank
but
you.
you were attracted to observability as solved. I just wanted to call out
I
like
was, yes.
what that materially means, right? Is that you can now see the way all of the things are connecting to each other, and it really gives you a level of understanding that what in this age of distributed systems that is there's nothing else out there that does this at this layer. It's amazing. It's amazing to
And
me.
yeah, it's such a game changer in so many ways. And yeah, is there okay, you talked about how is it safe, but is this eBPF verifier enough? Because any threat agents also are aware of the eBPF verifier and
Correct.
can write code to also dance with it.
Well, it's interesting.
Um,
I mean, so this is a fascinating new topic that we could spend like probably another entire episode on.
the safety of eBPF.
It's
Yeah.
not even really because at that point you're not really talking about the safety of eBPF. You're talking about
Uh-huh.
like how do we consider a threat model for the Linux kernel,
Uh-huh.
right?
Uh,
Because
yeah.
like and then we start getting into capabilities. We start getting into like who at you start talking about like as a threat model when a when an entity operating within the Linux kernel, a process, right, whether it's that bash process that you're using to interact with, when that process tries to is able to escalate its privilege to the point where it is able to then manipulate things like eBPF, because
Uh-huh.
it has to be effectively a root equivalent to be able to do that stuff. So if you are a root equivalent against the Linux kernel, that means that you can do
Uh-huh.
anything.
Yeah.
So then the question becomes: now that you have that level of privilege,
Yeah.
what are the targets that are most useful to you, and how
Uh-huh.
can we and how can and how can we determine one that that you have gotten to the point where you have that level of access, and
Uh-huh.
two that you have the ability to and two, is there any mechanism by which we can determine what you've done with that access?
Yeah.
That's where we get into Tetragon and a bunch of other stuff. But
Ah.
BoopKit is pretty cool. Yeah.
Tetragon. Oh. Is that a CNCF project? Tetragon?
Hmm?
Is
I said
Tetragon a CNCF
yes, it is.
CNCF
Yeah.
project? I need
Yep.
to we're doing for You Choose, we're planning our security chapter now. I'm not sure we have
Oh,
Tetragon represented.
I would
We
love
have a
I would love to be part of that somehow.
okay, we'll talk about that later.
Right.
We could spend an episode on Chris Nova's Boop Kit, which is a eBPF project that allows you to do hackery things on a node in a security research sort of way, of course.
Exactly.
Um, yes, yes. And we have a question. Why do we never hear about HA, about high availability with Cilium?
Why do we never hear about high availability? So this is a bit of a rabbit hole, but let's take a shot at it.
Okay.
So when we consider things like high availability, we're trying to generally solve a set of individual problems. We're trying to solve a specific set of problems. So high
Uh-huh.
availability could mean from one particular pod, I want to be able to talk to a bunch of other pods. How do I actually handle load balancing across those other pods? That load balancing mechanism in the middle represents a functionality of high availability because you have multiple things that can support it at the same time. I don't know if I want to record this piece because I want to save all this for service mesh.
Oh yeah,
But
yeah. I get it. I just noticed it was going up off the
okay, got
top.
it. Yeah.
So yeah.
But then other high ability piece, right? So when we talk about Cilium and perhaps Cilium itself having high availability against the Linux kernel, what would that mean, right? Cilium is the ability to write and inject eBPF programs into the Linux kernel, but there's only just the one Linux kernel that Cilium can affect. And this is a distributed system because we're talking about all of the nodes in your Kubernetes cluster. There's one Cilium agent per individual Linux kernel, and it's configuring each one of them directly. So high availability in that case wouldn't necessarily apply because there are no more resources about which to balance across, right? It's just a matter of resiliency at that point, which is different. Resiliency means if the agent dies and the kernel still lives, it's the agent and to be able to pick everything back up and continue if the agent comes back to life or if it is upgraded or changed. And what happens to all of those eBPF programs that were in the kernel the first time, right? Like, do we become aware of them? Do we have to pull them all out and put them back? Like, all of these things become questions about resiliency. But so high availability is like asking a question of high availability is in a way like pulling a chaos bomb and throwing it into a discussion. It's fascinating. We could talk about it in pretty much any dimension. Cilium
cool.
as a
So let's
service
talk about
mesh.
service mesh. Yes.
Yeah. So service mesh is really an interesting thing because it is a set of specific use cases. So let's query our nice. So I thought that was going to be the internal portal. So I was reading the comments. So
yes.
Let's ask the audience.
Yeah.
My Cilium. Yeah.
My Cilium, yes. Cilium service mesh. Yes.
That's because Taniwa is a fun guy.
I've picked up on that. Yes.
I got it.
I'm with
I got a good groan for that one. All right. All right. What are the use cases of service mesh? Let's ask the audience. I want to hear what the audience has to say about that. And I'll list a couple. I'll take some of the low hanging fruit, and we'll go from there.
Okay.
Use cases of service mesh are. One of them is encryption. Encrypting traffic back and forth between workloads.
So people call us MTLS, right?
Yeah.
Cool.
One of them is advanced load balancing.
Okay.
One of them is observability. I want to understand for a given connection or for a given path between two pods, how many of those connections resulted in a 200, an HTTP 200 error code versus like a 400 or a 503. I want to understand the health of a given web service. How many responses is it able to respond to? How many responses per second is it able to give it to us? How many errors in that same period of time were presented, etc. Right? So that level of observability, those golden metrics, as they call them, are important to us. What are some other use cases of service mesh that are out there? I'm curious, like if we see any more in the chat.
Can policy be written at a service mesh level?
It can, right? So layer 7 network policy is a good example of that. So let's say, so you can say L7 network policy, and we'll get into what that means as we get into this section. And then Taniwa points out canary deployments, which I think is actually an advanced load balancing use case, but we can put it in here. Or percentage-based load balancing is another way of thinking of it, but we'll talk more about that one, I think. Service discovery is an interesting one.
Oh, nice.
Fundamentally, it's like kind of already there in scope of Kubernetes. All right. Advanced service discovery. Fair. Okay, so let's start breaking these down. Let's start with encryption.
So
Cilium actually has and has had for a long time a number of different ways to encrypt all traffic in transit. And I want to describe like why people want this, because in my experience it's a pretty interesting topic. So let's just say encryption. Let's break it down. Use case encryption.
Okay. And this also would have to do with certificate management
Yeah.
too.
But first and foremost, we're talking about encryption. So the use case of encryption is typically a what do you call it? A not conformance, but in regulated environments, you are required to encrypt traffic in transit.
Okay, so to comply with some sort of regulation.
Yeah.
Yeah.
So typically speaking, compliance is kind of the word I'm looking for, but it's not really the one specifically that I was trying to think of. But yes, so in regulated environments, in secure environments, you are required to encrypt traffic in transit. In this way, and partially this is because you can operate a Kubernetes cluster or these compute environments in areas that should be considered to be untrusted, right? And that means that, like, the traffic moving back and forth between the routers of the internet, for example, would you trust that there's no entity on those routers that would want to capture traffic that's happening back and forth between those routers? Or would you want to ensure that traffic moving back and forth between those routers is all encrypted traffic? Right? And from a security mind perspective, everywhere I could have encryption, I want to have encryption. I want to encrypt everything that hits a wire before it hits the wire, as close to the source as I can get it.
Yeah.
Right? Then that way I can be sure that even if traffic is in an untrusted environment, that anybody capturing that traffic to try and perhaps pull information from that traffic would have to be able to decrypt that traffic. Right? And so that's where a lot of service meshes have seen an incredible amount of adoption, because service mesh is one of the mechanisms by which people can check that box. They can actually say, I'm encrypting all of the things because I have created a new pod. I've leveraged this service mesh mechanism to ensure that all traffic back and forth between these things is encrypted. And specifically, I've done that without changing my application.
Oh, yeah.
Right? I haven't given my application a certificate and said, you must encrypt. I've said, look, you do you.
Yeah.
I'm going to handle all of the encryption for you. Right? So Cilium can do this. Can do this in two different ways. Cilium can do this by basically opportunistically encrypting all traffic. Mallory in the middle, nice. Cilium can opportunistically I'm sorry for giving you these. I'm always using these crazy multisyllabic words. What the heck? Opportunistically encrypting all traffic with WireGuard,
Excellent.
or IPsec. Yeah.
Okay. IPsec is okay. You can tell me what those things are, please.
Yeah, these are two different technologies. I know it makes me sad though, Taniwa. It makes me sad. That's an unfun fact.
You can't use WireGuard in the U.S. government, so it has to be IPsec. And also, hello, Code with Sean. Glad you're here. Thank you for coming, friend.
Yay!
Okay.
All right. So we can do that.
These are two technologies to encrypt traffic.
Yeah. And basically what they do is they implement their encryption kind of at the node layer. That means that traffic that is leaving the node, even if it's destined for another node, will be, I mean,
Mm-hmm.
specifically if it's destined for another node within Kubernetes, will be
Mm-hmm.
encrypted in transit back and forth between those nodes.
Mm-hmm.
And there's basically two different implementations of a way to do this, right? Like how you go about encrypting it, and the different implementations are different in a variety of different ways, but fundamentally for our purposes, they solve encryption back and forth between workloads.
I guess I don't understand if it's a node to node thing. Like, what about if the two workloads are on the same node? Is that encrypted?
That's a great question. And this actually, again, goes back into the threat model thing, because this has come up
Uh-huh.
just recently in some of the newer FedRAMP compliance issues, right? Now, if we think about this, if these two processes are on the same node, and
Uh-huh.
we're basically allowing for socket-based load balancing to move back, to allow traffic to move back and forth between them,
Uh-huh.
the
Yeah.
only surface that we would allow for, the only surface that is not encrypted is basically socket-to-socket connections.
Uh-huh.
Right?
Okay.
Which on a host is pretty normal. Like if the attack,
Ah.
if the threat model includes you being able to capture network traffic on a node itself,
Uh-huh.
that can actually be like, why, if your threat model is, I have enough privilege to be able to capture network traffic happening on an interface within the node,
Uh-huh.
then you actually have a lot of more valuable targets that are available to you without dealing with trying to capture traffic on that node.
Okay.
Right? There are credentials lying around on file systems. There are there are environment variables that include usernames and passwords to databases that are adjacent to where you're located. Why on
Okay.
earth would you spend your time trying to understand what's happening back and forth between two applications at the network layer? While you could, there are just
Uh-huh.
much more valuable targets than that.
Okay. Fascinating.
Right. And so while we don't generally encrypt back and forth between two processes on the same node, what we do is we
Uh-huh.
reduce the attack surface of that by allowing for socket-based load balancing between them.
And when you say socket-based load balancing, you're talking about this
Yep.
pod-to-pod connection that's available within Cilium. That's different
Exactly.
from.
Yeah.
So then I guess maybe you covered this, but so with a traditional CNI, when you have to go pod host, IP tables host pod, does that need to be encrypted? Or is it the
So
same thing where you have more interesting stuff to get if you can get at that?
it's the same thing. If you have a root
Okay.
level attacker, that root level
Okay.
attacker has access to way more valuable stuff than the network data.
Okay. Fascinating. Cool. So that's Cilium can encrypt traffic in two ways. The first one is with WireGuard or IPsec. And then what's
Yep.
the second one?
Mutual authentication.
So you're encrypting with, is it opportunistically?
In the first one, yes, and the second one, no. We'll start with mutual authentication.
Okay. And this is encrypting with mutual authentication.
Yeah, well, this is still encrypting with WireGuard or IPsec, but
Okay.
before we allow for that encryption, we ensure
Mm-hmm.
that connection is encrypted, and we also authenticate between workloads. So we're basically, I guess the best way to do this is to break down what MTLS is.
Okay.
So MTLS is an umbrella term. Do I have enough
Mm-hmm.
space to do this? This is why I wanted to jump into this, because I know that's going to take a little bit. So MTLS is, let's talk about what MTLS is.
Okay. I'm just going to write mutual TLS here.
Yeah.
And TLS is transport layer security.
Yes. And mutual
Yes.
TLS is a combination of authentication and encryption.
Yes. So this is where we're getting to PKI and private public key and infrastructure. Yes.
Yeah. But I'm not going to jump into a whole bunch of detail around that.
Oh yeah, that's a huge rabbit hole. Yeah.
I've definitely given those talks.
We did an episode on Cert Manager, if you're curious, where we
got
nice. Deeper into Excellent. PKI. So
who did the Cert Manager one?
Ashley Davis.
Very cool.
He's great. Yes. So mutual TLS is both identity and encryption.
encryption. Yes.
Mm-hmm.
And they're coupled. Basically, it means that with mutual TLS, you have a client certificate and you have a client certificate effectively on both sides, but and you have a server certificate. So when you make a new connection to another entity, you're saying, hey, other entity, here is my client certificate. You can encrypt traffic back to me leveraging this public key. And when you interact with them, they look at that client certificate. Should I trust this? Is this is this client certificate signed by a authority that allows me to trust that this client certificate is who it says it is? And if it is, then I'll go ahead and allow the connections to establish, and I'll reply with my own server certificate so that it knows how to encrypt me. And so there's this mutual authentication mechanism where both sides, the client and the server, are verifying that each of the others is trusted. Right? And that's the authentication piece. That's where we're saying, you have given me your ID. You have shown me your ID. I have shown you my ID. We have agreed that we trust each other at least far enough to establish a connection between each other. And then with MTS, leveraging MTLS, you generally establish a secret that you will use to encrypt traffic back and forth between yourselves during the period of this conversation. I've shown you my ID. You show me your ID. We're going to establish an encryption secret that we will use to encrypt traffic back and forth between us as we continue our conversation. Okay. And this is what I mean by it's coupled, right? So you have authentication and you have encryption all in one thing. With Cilium, we decouple this. So with Cilium, we say, we want that mutual authentication piece. We want you to be able to prove on both sides without modifying your application. We want you to be able to prove on both sides that the identities that we have are trusted within each other. We can trust each other, and we're going to allow for this encryption to happen. But the encryption piece that we're going to use between them is going to be one of the existing encryption models that we have, like an IPsec or WireGuard.
Okay.
So authentication, MTLS. Encryption, WireGuard, IPsec. Okay. And the reason there are a couple of different reasons, or a couple of big benefits of decoupling this. One of them is that with MTLS, this traffic has to effectively be HTTP traffic. But that isn't actually true of all workloads within your Kubernetes environment. Right? Some of that traffic might not be HTTP traffic. How would you secure that traffic? If we're leveraging IPsec or WireGuard to handle the encryption piece of it, then we can actually encrypt anything back and forth between these workloads. Decouples authentication and encryption. Yeah, or encryption and authentication, either way. I like Code with Sean's reply. I'm going to tell you what MTLS is, but first, who are you, and can I trust you?
And also, I'll only tell you in a secret message that only you have the decoder for.
Yes.
Okay.
Oh, authentication and encryption. Oh, wait.
And then, and that has two benefits. And the first benefit is you could do other protocols besides HTTPS.
Correct.
Okay, and what else? And what else?
And another benefit is that because we can leverage IPsec as an encryption protocol. This is a neat one because it allows us to say that the encryption the encryption that we use to protect the data back and forth between these workloads can be FedRAMP or FIPS compliant, which is big, right? So in regulatory environments, right, MTLS can be FIPS compliant, but IPsec has been FIPS compliant for quite a long time. So we can leverage
IPS.
FIPS,
Okay.
compliant.
Cool. Thank you, Taniwa.
What's the acronym? I wonder if he knows. He probably does. We're not going to write it.
Yeah.
Federal Information Processing Standards. It means basically that these, yes. Hey, whoa, got it. Nice. So this is actually, this is the government saying, when you want to keep something safe, here are some standards by which we will measure whether that is reasonably safe.
So before Cilium, before Cilium, how was this FIPS compliance, not FIPS compliance?
I love it.
Meaning I'll comply with whatever that draft tells me to do. How was this done? How was FIPS compliance done before Cilium?
So it's still, it's still being done. And so one of the things that, so I guess this is a bit of a side note. So the way that FIPS compliant is achieved is through a set of standards that describe like how we go about encrypting traffic back and forth between these things. And technologies that are leveraged to encrypt this traffic are measured against that set of standards. And there'll usually be a document that says IPsec with these particular libraries is compliant. And so for you to be able to become FIPS compliant, you have to use some technology that has been selected and written up in the way that it has been written up to allow for you to be able to reach a level of FIPS compliance. So while it is true that like you could leverage IPsec, for example, just to encrypt traffic back and forth between nodes, just like we do, and you're leveraging a Linux kernel and a set of libraries that make it compatible, you could do that, and that would be FIPS compliant.
So you might do that outside of a service mesh implementation before, and now you can do it as part of your service mesh.
But now in this crazy world of container orchestration, I would say that the federal entities are struggling a little to understand the attack surface as it relates to this new world, because the attack surface has really changed, right? Containers are not virtual machines, right? Virtual machines have their own Linux kernel that they have to protect individually of themselves. Containers all share the same Linux kernel, right? All of those file systems are all held and accessible by the same Linux kernel, which means that like the attack surface is very different than a bunch of individual computers.
Yeah, than when the FIPS standards were probably written. Yeah.
Yeah, and so they're trying to change the FIPS standards to adjust for this new world. But one of the things that they ask is like, can we encrypt back and forth between all network entities, which means all pods? And we're like, I mean, sure, but honestly, if the attack surface, if the threat model is that somebody has that level of access to a node, you're not encrypting the traffic.
Yeah.
Like there's an apple pie sitting right there. You know what I mean? Like, what are you doing? Yeah.
Yeah.
So that's use case encryption.
Cool.
Let's do a use case advanced load balancing.
Okay. Where's my head?
I love these discussions. I feel like they're great because they're just super wide ranging, and they're always so much fun to kind of get into.
Thank you. I think so too. I like being able to ask for all the context around a statement, you know?
Yeah. I think I said this last time, but I'll say it again here because I think it's one of my favorite things. So I often tell people, like I have one of those brains where I want to learn everything about everything, right? And you I know also have one of those brains.
Yeah.
What I've come to over time is that I can only ever learn everything about everything by teaching it.
Oh.
I can never learn everything about everything in a vacuum. And that's because honestly, without the perspectives of others, I would never come up with the question that advances my own learning.
Yeah. Like you don't
right?
know what you don't know.
Right.
Yeah.
I can only learn it so far with my own perspective,
Uh-huh.
because these are only the questions that I would ask. Here's the questions that
Uh-huh.
I would ask, and they're good questions, but they only get me
Uh-huh.
so far. And when you ask me questions or somebody else asks me questions, and I'm like, whoa, I never thought about that, right? But that opens up a whole new area of things that I can learn about in a particular context that I would never have come to on my own,
That's so
right? And
cool.
I
Yeah.
love that.
I love it too.
All right. So advanced load balancing. So we have implemented in Cilium a thing called Gateway API.
Uh-huh.
And
And
Gateway
there's a
API, there's an
just
episode
for
on Gateway API. Yeah.
yeah, yeah. Mm-hmm.
Well, that wasn't with Nick though, was it?
It was, yeah.
Oh yeah. Nick is the
Yeah.
best. Nick works at
Nick is
Isovalent.
the best. Uh-huh.
Um, so Gateway API is a new version of Ingress that allows for much more advanced Ingress models.
Mm-hmm.
So we should probably capture like use case advanced load balancing Gateway API.
Should I write Cilium implements Gateway API?
Sure. Cilium implements Gateway API.
And it's an official implementation,
Yes.
which means you had to pass some sort of compliance test, if I remember correctly.
Correct. Yeah.
Cilium did. Okay, and then this means, what does that mean?
So that enables people,
Mm-hmm.
consumers, to actually have more advanced load balancing mechanisms to solve situations like percentage-based routing and canary, which is the canary routing mechanism. Advanced load balancing and ingress, we'll say.
Cool.
Which gives you a
So,
lot of capability around like more advanced load balancing that people would go to a service mesh for. So in the service mesh case, you might want to be able to say, consumers that are coming into my Kubernetes cluster or into my service that have this cookie, I want to split the traffic 30% to service A and 70% to service B. This is an example of advanced load balancing. And
okay.
I'll base that decision about where to send that traffic on some particular characteristic about the traffic. Like it might be sourced from North America or sourced from the Silicon Valley. I want it to go to 30% of the traffic to go here, and sourced from California, I want 70% of the traffic to go everywhere, to go to this other service.
I could route based on headers, and I can divide it up based on percentages.
Yeah, exactly. I can do all kinds of things like that with it as it relates to things for this type of traffic. And this is important because this is actually one of the use cases of service mesh. This is why one of the use cases of service mesh is to handle this type of advanced load balancing. And
interesting, because I thought it was that was more of a well, I think it's kind of like overlapping, but I would have thought it would be like an Ingress project that's going to be called on to do this sort of advanced load balancing where it's coming from outside of the cluster.
This is Ingress.
Right, yeah, that's what I'm seeing.
Yeah.
So, but is more and more just Ingress and load balancing just the same projects? Like the Ingress projects are doing or I said load balancing, but I meant service mesh.
I think that more and more. So this is actually kind of an interesting thing. So we know that Kubernetes has this object called Ingress, and the Ingress API has existed for a long time, and it is probably, I would assume, I think that Ingress API object was like the longest one in beta. I could be wrong about that, but I'm pretty sure that it has been the longest Kubernetes API in beta, because we realized pretty early on that the complexity with which people want to configure Ingress is significantly more than we have captured with the Ingress API. Right? And that means, so how do we move past that? How do we actually, so we
Yeah.
have to let the ingress API be the ingress API, and then we have to determine what the next thing is to be able to help solve some of those problems. And that's where like
Gateway
gateway,
API.
yeah, exactly, right? It's like V2 or V3 or whatever V you want to associate with it. Come in, because we're like, you know what, like it's clear that like there's a lot more capability here than we are currently addressing, and so we have to think about that.
So I guess my question is, why even have an ingress if you have service mesh that also does ingress? Why have a separate project for that?
And typically speaking, people will pick one or the other. They will not do both.
Okay.
Right? They'll say, you know what, my needs are advanced enough that I need an API that gives me more capability than just the ingress object. And so for my Kubernetes stack, I will include Linkerd. I will include Cilium Service Mesh. I will include Istio. I will include whatever it is that actually solves that particular set of requirements that they have for their ingress traffic.
Fascinating. Cool. So is there something else we want to say about Cilium? Ooh, you're like, it's like a party over there.
I know. I'm rocking out. There we go. That's better. It's because the sun, like this time of year, the sun is like directly behind me.
Okay.
So my little lamps are like struggling to keep up.
So is this wrap it up for advanced load balancing use case?
I think it does a pretty good job. And then the next piece I want to talk about is observability. And actually, let's just do a quick one on layer 7 network policy, and then we'll go into observability.
Okay.
So L7 network policy means that I want to be able to control the traffic at the application layer between things within my cluster. And that means that I might be able to say, this particular application can access this web gateway or this web API, but only on specific paths and only with particular HTTP verbs. Like you can do a get, but you can't do a delete. So the HTTP use case would be like being able to do a get, but not a delete. And it would be only on specific API paths.
So control traffic between applications.
At the application layer.
Is at the application layer different from saying between applications?
Yes, because between applications, you might just want to be able to say, I want to allow all traffic or not allow all traffic. But at the application layer, you're saying, I want to allow this very specific traffic, but only that.
Okay. I see.
And that means that, like, I want to be able to allow HTTP traffic to move back and forth between a client and a web service, but only on specific paths. And I may want to allow for gets, but not for deletes.
Okay.
And this is something that has existed in Cilium for quite a long time. Right? And this use case has been solved by Cilium for quite a long time. And we can solve this with HTTP traffic. We can solve this with Kafka traffic. We have protocol-specific protocol-specific mechanisms for handling different protocol. We have different protocol. How do I put this? Different protocol parsers that handle this sort of stuff.
This is solved by Cilium and for many protocols.
Yes.
All right.
Now we do observability. And then I think we're actually, wrapping it up. Pretty exciting.
Good thing, because
I think we did.
it's
I think we did
gonna
great.
be time to. Oh
Yes.
yeah, heck yeah.
I think that pen might be dying though.
Yeah. Do you know I get a new set of pins out for every episode, and we're using it up.
All right.
In a good way. Use case observability.
Now here is where we really shine.
Uh-huh.
So most service meshes, when they implement observability, they can only do deep packet inspection to be able to accomplish it.
What is deep packet inspection?
I know, right? So deep packet inspection means that, like, when I want to pull relevant context out of a network stream, I have to actually look at every packet, every session that's going through, and capture that context from it as it is passing through the proxy that is my observation point.
Oh. Okay.
Cilium and Raisin.
So the observation points in other service meshes are the containers that are running alongside the pods.
Correct. Yeah. If it's a sidecar, model, like Ambient, for example, does a different thing than this. But yes, you're right. If you're using a sidecar mesh, then that sidecar is your only observation point. Right. But Cilium's observation point is the Linux kernel.
Yeah. And so the benefit of that, besides like the ease and like the real time, like the native kernel speed aspect, you also maybe have the fact that it's all being gathered at the same place as opposed to a lot of different other points all around the system and then needing to be moved to one place.
Mm-hmm.
Those are the two I'm inferring. Yeah.
And the other one that is a big one is context. In observability, context is king, right? Like that's it is like if you're gaining nothing else out of my observability stack, it should be context, relevant context about what's happening. And we have way more context because we're observing everything that happens, not just at a networking layer, but also at an application layer. I can tell you, so as an example of this, most service meshes can tell you that the traffic came from a pod. I can tell you that the traffic came from a process.
Oh. So you can see network layer events alongside application layer events.
Yes.
And I like that. Like other, you can tell it came from a process, not just a pod.
Yeah. And that means that, like, I could actually, like, say, for example, you have somebody that is exfiltrating data from your cluster. They have managed to get a reverse shell on some particular pod inside your cluster. While most observability tools would be able to show you this bunch of data left this particular pod at this time, I can tell you it was this bash process. They ran this command. They connected with this particular FQDN and sent this traffic at this point. there's a lot more context, a lot more data that we can provide to you.
Cool. And
so observability is one of those things that, because it's like a native, it's like a first class thing from the beginning, right? Gathering context in the Linux kernel has always been one of the most powerful use cases of eBPF. And so when we think about leveraging eBPF to gather context to solve for things like observability, we are in a incredibly unique position to be able to do that. Pretty cool.
are there any use cases where more traditional service meshes that aren't eBPF might be better suited?
I think it's a hard one. I think that so we've talked about the way that we think about encryption, right? In our particular case, we're decoupling authentication and encryption, and we do that because for the benefits that I've highlighted. But some folks probably, I mean, perhaps in their scenario, MTLS is enough, and it's actually like, and they're comfortable with it, and maybe that's why they want to go about it. It's a hard one for me to get my head around, because I've been an operator for a long time. I've worked in developing and managing platform infrastructure for a number of companies, including Apple and others. And when I look at this and I see everything that Cilium is able to do, and this means that I'm installing one product and configuring one product and managing the lifecycle of one product and one API, I'm like, why would I deploy another thing that doesn't measure up, right? Like, why would I deploy 2 or 3 different things to solve each of these individual use cases instead of just using a tool that I can manage the life cycle of once to manage this problem? So I have to admit, I will honestly admit that I'm biased in this particular case, but when I look at it objectively, I'm like, it's hard. Like, you know, it's one of those sunk cost fallacies in some ways, right? Like, because you have done something, but just because it took you a long time to do a thing doesn't mean that it's inherently the right thing.
Yeah. And so if you wanted to implement Cilium's functionality using a combination of other tools, you might have a service mesh, you might have a runtime policy engine, right?
You might have an APM, you might have like Sysdig, you might have like, there's a variety of different things that you would use to solve all of these individual problems.
You might have an Ingress
controller separate from, you might have something that implements load balancing like KubeVip, or you might have something that, or you might be using the load balancing mechanisms that come with your cloud provider, right? Like there's a ton of this stuff that is all that we do all in one product or one capability, where like just so many other things out there that do it. And the benefit in our scenario is that so many of these things all come back to what are the use cases that we can implement with eBPF. If you could change the way things work at the kernel layer, then like what would you change to make things more secure, to make things more observable, to make things more to give you more control or capability in the networking stack, at the application stack, all of those things.
And that can be answered on a per organization basis.
100%, yeah.
Which is cool.
Yeah.
All right, I wanna start the recap. Does that sound good?
Woo!
Let's see how we got this. Yeah. All y'all in the chat, if you have any final questions or comments, now's the time to share those feelings. It sounds like a couple people are away from keyboard. But so first, to understand Cilium and the power that's there, first we need to understand eBPF, which eBPF stands for Extended Berkeley Packet Filter. And what eBPF is it's a kernel technology that enables the user to inspect and manipulate any call to the Linux kernel. So when you said that, like I maybe got a serious face, my jaw dropped a little bit, and you were just like, I can see what you're thinking. I know you're like, how is that safe?
I was thinking it too. When I first saw it, I was like, wait a minute. Yeah.
And that is exactly what I was thinking. And so how is ePPF safe? And so there is an ePPF verifier before the Linux kernel technology, the Linux kernel stuff is able to be observed and manipulated. First, it has to be verified. And so you're verifying that it's not an endless loop and verifying in various ways that the code is safe and that it won't crash.
Correct.
So this every program that gets injected into the kernel has to go through this verifier, and that's how eBPF is safe. So now we understand eBPF, then we need to understand Cilium. So Cilium, before I did this episode is in the context of a series of service mesh episodes. So in my mind, it was like, oh, Cilium's just another service mesh. But that's not how we define Cilium, and that's not all Cilium is. What Cilium is an entire networking technology that solves a lot of networking related problems, not just service mesh. But it does do the three big service mesh things that all the other service mesh projects have talked about, which is networking, security, and observability. And Cilium can do that in both cloud and legacy environments. And at native kernel speed, like a superhero. So then we talked about how Cilium does its thing. And this is, we talked a lot about pods and IP tables, and this is like a Kubernetes context. And how Cilium does its thing in Kubernetes context. When a kubelet creates a pod, the kubelet reaches out to the CNI implementation. CNI stands for Container Network Interface. And so in this case, Cilium, and the kubelet's like, give me a networking stack for a pod. And so Cilium does that, gives the IP address and other things. And it also generates an identity for the pod. And so it also attaches an eBPF program to the pod network namespace. So I learned in terms of networking, you can think of like the host has its own network, the pod has its own network, each container has its own network. So we're talking about it at the pod level here. An eBPF program is attached to that. So then you said, rather boldly, observability is solved. So we went back to point out it really is mind-blowing that observability is solved. So basically, the eBPF program starts generating all events that are happening in that pod name service, not pod network namespace. It's generating it at the kernel level. So now we can see everything that's happened. As spoiler alert, as we talk about later, you have way more context because you can see the networking layer events alongside all the application layer events. So the eBPF program that's attached to the pod network namespace starts generating all those events. And so examples of events are a pod tried to reach outside the cluster, or a pod opened a certain network socket, or a pod tried to talk to this other pod. Those are examples. So that's the observability piece of talking about what Cilium's networking technology. Cilium, so the security piece is that Cilium can implement a network policy or many network policies with eBPF. So this is the same eBPF program that gets attached to it that we already talked about. So this will compare every single event that's generated that we talked about in step 4 against that network policy. So it's doing it at it considers it at the packet level, not the session level. So with other technologies before this, what would happen is when a session started between two in-network entities, that's when it would be compared against policy. And once it passed policy, it's not being watched anymore. And it's going to live at that level until it dies and is restarted. So your policy could change, but if the session's going, the session's not going to update, and you can be running old policy. And so with eBPF, it's doing policy at the packet level. So therefore, when a policy changes, bam, it changes immediately. Bam. So then we talked about Cilium. So that's Cilium and security. Now Cilium and networking, we talked about socket layer load balancing. So this is news to me, but when two pods want to talk to each other and they're running on the same machine, in the past what had to happen was a pod would talk to the host would talk to the IP table would talk back to the host, and then the host would talk to the other pod. And that's how those two pods would communicate with each other. It was quite a long process. And so now with eBPF, you can open up, you can trust a network socket that goes straight from one pod to another pod and skip all that IP table, all those shenanigans. And so that socket, so what like tangible benefits do you get from communicating that way? Is it just faster, or is it what performance do you see that's different once you implement that part of it?
Specifically, these things are actually more affected by things like latency, right? So latency is typically described as the things that affect a packet's life or a session's life between the establishment and every other packet that's coming along it, right? So anything that would affect that life would actually cause the latency between those packets to slow down, and it may cause things to actually, kind of slow down in general. In our case, we're saying we're going to allow this session to establish, and then these two processes are just going to communicate with each other at effectively the rate at a socket that a socket can support, which is always going to be much lower latency than having to go back and forth between user space and kernel space and user space and kernel space, etc.
So improved latency, is that just faster? What's it better? Less latency?
Better. Lower latency and those sorts of
lower
things.
latency. Cool.
Code with Sean has put up a note that says, with so much to configure, are you glad K8s is not from IKEA? And I have to tell you that there is a great talk at KubeCon Valencia from an engineer who works at IKEA who has implemented Cilium, and he absolutely embraced the meme. He did his whole talk was IKEA themed. It was beautiful.
I love it. Okay, so and then we talked more about networking, because Cilium is ultimately a networking technology, and that's so Cilium can also be a kube proxy replacement. So first, let's talk about so kube proxy is a process that runs on every node, and it's shipped as part of Kubernetes. And it implements services like cluster IP and node port using IP tables or IPVS, which stands for IP Virtual Server. So Cilium, so with kube proxy, like the old version, the IP tables, it was using IP tables again, and those are constantly updating and reloading, and it maybe made the system slower to converge. And so Cilium doesn't need to use kube proxy for the reasons that we discussed before. Is that true? Just because it can open up the socket right on the node, on the pod, I mean?
And because we've done a ton of work to actually implement all of the functionality of kube proxy in eBPF. So instead of now having a kube proxy agent, you just have the Cilium agent doing all of the work of kube proxy.
Cool. So Cilium can replace kube proxy and is especially useful in high scale environments, because that IP table is basically one huge long thing. And now we have these connections, all these rules are not one unit anymore. They're atomic rules. And so every time a rule changed when it was like IP table based, then the whole IP table would have to reload. And now anytime a rule changes, it's just that one rule that changes. So this has like lower CPU usage. You have zero convergence time. And then again, those atomic networking rules. And then finally, Cilium can also handle load balancing, BGP, which stands for Border Gateway Protocol. BGP announces IPs and data centers. But Cilium can handle IPv6. Cilium can handle egress gateways. And basically, Cilium in general improves connectivity between Kubernetes clusters. So we're talking a lot about within a Kubernetes cluster. So between Kubernetes clusters and also between a Kubernetes cluster and the world and everything. Connectivity, networking, doing a thing, all that stuff. Very technically. And so then we dug in about Cilium as a service mesh. And I like how you handle this. You asked the chat, why do you have service mesh? What are use cases for service mesh generally? And what we came up with is like encryption, specifically MTLS, advanced load balancing, observability, L7 network policy, canary deployments, and service discovery. And so we went through these use cases and talked about how Cilium handles each one. So for encryption, encryption is especially needed in regulated environments. And so Cilium can handle this in two ways, or does it both ways, which is one, it opportunistically can encrypt all traffic with WiredGuard or IPsec. So this is node-to-node traffic, and you explained to me why traffic doesn't need to be encrypted between services on the same node. And that's because there's much more exciting things for a hacker to do if they're that deep in your system. And the second thing is mutual authentication. So Cilium so with MTLS, the authentication and the encryption is all wrapped up in the same mechanism, the same like PKI infrastructure situation. And now here with Cilium, we have the encryption decoupled from the authentication. So that means you can use other protocols. I wrote besides MTLS, but what I meant was HTTPS. Besides HTTPS, which is a big deal, like a lot of places want to use gRPC or whatever. It also can be FIPS compliant, which I think it hurts my soul to not write an acronym on the board. So I'm just going to do that real quick. Okay. FIPS, Federal Information. Is that right? Processing.
Yep. Federal Information Processing Standards.
Cool.
I didn't want to get you with like all of those multisyllabic words.
I appreciate it. Now that I know, I can make a little space. So that's FIPS. So it can be FIPS compliant, which is a big deal that some orgs really need to worry about. And then, so then the next use case we talked about was advanced load balancing. So Cilium is an implementation of Gateway API, and Gateway API is, you could think of it as Ingress v2. So it's the SIG networking community within Kubernetes created Gateway API as a set of resources to better implement the more complex use cases of needing to move traffic around in Kubernetes than what the native Ingress object can handle. So because it uses Gateway API, it enables more advanced load balancing mechanisms. So an example we gave is like a percentage-based load balancing, or load balancing based on the headers of the requests, that sort of thing. Next use case is L7 network policy. L7 is a punk band I listened to in high school, but besides that, it's is the application layer. So you can control traffic at the application layer. So an example we gave is if there's HTTP traffic, we could allow that between X client and X web service, but only on the specific path and only for GET, not delete. Like that sort of rules we can make with Cilium. And it's solved by Cilium, and it's solved by Cilium for many different protocols for traffic within your cluster. And then the final use case was observability, which is solved. We did it. Check. Cilium really shines in this observability use case. So that's because other service meshes use deep packet inspection, and they're doing this observability if it's a sidecar service mesh, like alongside the application, as opposed to Cilium's observation point is in the Linux kernel. So that provides all of that context, the networking layer context, alongside the application layer event context. So a great example you said is Cilium can tell, like if you could tell there's regular service mesh could tell there's a nefarious event that's coming from a certain pod. But Cilium can say, hey, this nefarious event is coming from this process and this pod. So you have more granular observability. I have a question. Is there any compute cost that comes with that more granular observability?
So from the perspective of that, there's no compute cost for gathering the context. The cost comes in when we have that context and we want to be able to get that context down to user space so that we can leverage it in in user space, so we can actually take those events and do something with them.
Yeah,
That's the big challenge.
That makes sense,
Right.
because you have more information, therefore it would take more compute to do something with that information. Yes?
Yep, agreed.
Tani, who I haven't been watching your comments, but you've written quite a lot since I've looked. I was in the zone doing the recap. We talked about egrets instead of egress just yesterday. I was talking with a buddy about that.
Nice.
In the long run, we'll get there. And Tani, who are you? Are you like a maintainer of Cilium, or what's your? Tell me who you are, please.
Tani, can I tell them who you are? Because you've actually been Fippy, and I know who you are.
I'm not in Cilium. Okay,
He's not in Cilium. Yeah.
Okay. Whatever you want to say. I don't mean to put you on the spot, but you know so much. I was curious if I'm talking about your stuff, or like, for example,
he's Cilium
like
adjacent.
There. Yeah. Cilium adjacent. Awesome. A backronym, the definition for FIPS, backronym, because no one uses it. I haven't heard that term backronym before.
Yeah.
I want to start a KubeCon band called the Pods. I'll be in your KubeCon band. We can scale the members based on availability. When one quits, you just pull in another one. It doesn't have to be the same person. Oh.
I love this whole idea.
Heck yeah. Outside of kernel CPU time used, can we even measure? I think this was in relation to my question about, is there a compute cost to having this extra observability? Yeah, so that, I think that was maybe a question for you. Can we even measure the compute cost
of eBPF?
I think, I was asking, like, because, like, what's the extra compute cost of being able to have this more granular observability?
Yeah, and I was saying that there's no particular cost to actually gathering the context of getting the data, because we're getting that data from the event itself, and there's not really much. There's no additional cost to that piece of it. What's expensive, though, is actually generating all of those events, getting them down into user space, and then associating those events with the relevant data that you would actually want to know about. That part can get a little pricey when it comes to, like, because we're manipulating data, we're manipulating all of this data to get to a place where it's useful when it gets down to user space. And that part can be expensive, but it really comes down, the expense is generally memory, not in CPU time. So the expense in memory, especially in modern compute systems, is more negligible than we really want to think about. You know, like it's ridiculous. Yeah.
Cool. I think we did it. I think we wrapped up this amazing Enlightning episode with just wonderful, wonderful people and learnings. So those of you who watch regularly will know it's time to put on some music and dance it out and say goodbye. Thank you so much, everyone, for being here. Thanks for watching the recording. Thank you, Duffie, for sharing your time and your immense expertise.
Thank you for inviting me. It's always a blast. It's been a pleasure hanging out with all of you, and I hope that we all learned something here. I know it's always great seeing all these new questions.
It's so good. All right, let's dance it out. Goodbye, everyone.
Bye.
Bye. Yeah, Duffie.